Hello, my name is Gary Kuan. I'm the optical system engineer for the Roman CGI. I am presenting the optical configuration design of the instrument, but there's a lot of people involved in the design work, in the procurement of all the optics and all the testing. So I'm just a spokesman here for that today. Outline. I'll try to go through this a little bit quickly. So the instrument is interfaced to the observatory. It is this. Is there a pointer on this? Yeah. Okay. Right there. There's the red box here. The telescope feeds through to the instrument from what we call a tertiary collimating assembly, which sits right above the chronograph. It provides a 40 millimeter diameter beam. The interface between the instrument and the telescope front end is at a pupil plane. The chronograph is a requirement for alignment is 0.5 millimeter in shear, pupil shear, and 1.5 arc seconds on the sky boresight. But those can be have correcting mechanisms to adjust for that. It's the clocking that we don't have any control over. So we have 1.31 milliradian of pupil clocking there's no corrective mechanism for that. So there's kind of a quick list of the key design requirements for the instrument. Interface of the maximum field of view, vignetted field of view, 4 arc seconds, 3 arc seconds, unvignetted field of view. We have an HLC chronograph as well as an SPC chronographs in direct imaging mode, in pupil imaging mode, with a slit spectroscopy mode, polarization imaging modes, 4 observing bands. Band 1 is our threshold band, and then with a plate scale of 0.022 arc seconds per pixel at the imaging camera. For controls, we have a fast steering mirror for pointing control at the entrance to the instrument, a focus control mirror to correct for defocus, 2 deformable mirrors for wavefront amplitude and phase control. For mode selections, we have a variety of precision alignment mechanisms or PAMs to swap out SPC shape pupil chronograph masks, focal plane mask or occulters, Leo stop masks, the field stops, all of the various optics and masks that, or the masks that AJ had just shown you in the previous presentation, as well as a whole bunch of color filters and a number of imaging optics. 2 deformable mirrors, 48 by 48 actuators, 1 millimeter pitch for each actuator, and it's intended to correct Zernike's 4 through 11 in the waveform. We also have a low order wavefront sensor centered at a wavelength of 575 nanometers, 128 nanometer bandpass, and able to send Zernike's 2 through 11. So here's the layout of our optical subsystem. On the left-hand side of the screen, I just put in the ray trace there with the gray boxes for the optics, as opposed to the CAD, which has all the various elements on it and gets a little cluttered, and the actual as-built instrument is even more cluttered and hard to see. The input to the instrument comes in here, and it hits the first optic, the fast steering mirror, and on this side it is right there. Okay, so here's a picture of the aligned optical bench. You can see if you look top down on that, it has a whole bunch of cables and optics mechanisms, interfaces, and it looks very cluttered, but it is a very complex optical instrument. So the front end of the instrument is where the most of the magic of coronography happens. It consists of two OAP pair relays, actually 2.5, so two full relays and then another OAP to produce the focal plane. We have, as I mentioned, the fast steering mirror, the focus control mirrors, the two DMs, and the shaped pupil chronograph masks on a precision alignment mechanism. And then there's another alignment mechanism, here that has the occulting masks. So the first two OAP relay pairs produce two internal pupil planes, one for DM1 and one for the shaped pupil mask. The third relay, the third relay produces a focal plane where we have the occulters and also reflects into the lower order wavefront sensor. Of particular note is here relay 1. Relay 1 consists of the fast steering mirror, two OAPs, the focus control mirror, and then ends at DM1. This was more complicated because the focus control mirror, in order to not produce any other aberrations other than just correcting for focus, needed to be on axis to the beam. And therefore, the reflected beam from OAP1 goes through a hole in OAP2, and before it goes to the fast steering, so the focus control mechanism, goes back, reflects off of OAP2, and then goes and produces the pupil plane at DM1. Note that the hole in OAP2 is only 9 millimeters diameter, which made it challenging to both fabricate and to align into the system. But you know, and Brian and Shelley will discuss this in the next presentation on the optical alignment of the optical subsystem. The back end it produces another pupil plane from the third relay at the Leo stop. After that, it demagnifies the beam to produce a collimated beam going into the imaging optics. Also at the focus of the fourth relay is the field stop precision alignment mechanisms. Also in the back end, after producing an exit pupil just after OAP8, the collimated beam goes through the color filter alignment mechanisms, and then the direct imaging and polarization alignment mechanism that holds all the optics for the variety of imaging modes, and then the beam proceeds to the XCAM or the exoplanet imaging camera. One more region of note for the optical design is the LOFUS. The LOFUS path consists of a quarter wave phase dimple that AJ just discussed on the occulter masks at the FPAM. That send the reflected light then goes through the what we call the lobe, the LOFUS optical barrel element, and then produces a pupil at the LOCAM, the lower wavefront sensing camera. Note that the lobe optics was originally designed to accommodate an off-axis path for the star shade, which had been dropped later on. But at the time that we dropped it, we decided just to keep the optical design as is and continue to use the on-axis path for coronography. All right, so here's just a couple of images, some images on these slides for the as-built optics. We have the fast steering mirror over here. Note that that was an original design and built for the Space Interferometry mission that ended in about 2010, 2011. So this may be the one component of that project that actually flies. Then the focus control mechanism here, deformable mirror, one shown, there's two of them. And then here's the low order wavefront sensing camera, which is identical to the exoplanet imaging camera. Precision alignment mechanisms. So the mechanisms themselves were contributed from our international partners, MPIA. Each of these, there's two different styles of PAMs. I don't believe we have a talk on them specifically, but as you can see, there's a whole bunch of masks and optics on each one. And I did a count of all the optics in individual substrates, not including all the individual masks. And we're looking at something like 268 optics in this system. And then you throw in some beam dumps and baffles and the cameras, the detectors themselves, and the number goes up, and the combination are pretty much endless. See, so you can see on the shape pupil alignment mechanism, the four shape pupil masks. The fold mirror there is used when we're not doing the shape pupil mode. The Leo stops here with a through hole in case you don't want to have a Leo stop there. All the variety of color filters with a dark mask in the center for blocking any light getting to the camera. All the optics on the DPAM, that includes some individual defocus phase retrieval lenses, the field stop mechanism that has the field stop array there, as well as some open apertures and an ND filter. And the focal plane alignment mechanism. There's just the plates shown here with the substrates bonded on. There are ND filters, as well as the four different substrates. And if you look closely, you can see all the variety of masks that are etched or created on there, as AJ had just discussed. The static optics, there are 9 of them. 4 of them were produced by our international partner LAM using stress polishing techniques. And then here's an example, or the picture of the OAP2 with its hole in the center, and the low order wavefront sensing optical barrel element. Okay, so kind of a quick discussion on the polarization, and I don't think we really have much time to go into this, but so we did assess the polarization aberrations coming out of the telescope, and it's something that we definitely need to consider. In the case of CGI, the residual of the cross terms of the polarization aberrations contribute on the order of in less than 10 to the minus 8, maybe around 2 to 10 to the minus 9 degradation in contrast. For CGI, that's okay. For something like HWO, something that we're really going to have to look into and consider ways to reduce the effect. There's more analysis on this in a paper by John Chris in JADIS last year. And hopefully we'll have some more discussions on that and analysis of that in the future, or presentation of that in the future. So for the optical performance and wavefront error, we had a couple of different steps in the testing of the optical subsystem. Initially, the entire optical system was aligned without the deformable mirrors in place. We had 2 flat surrogate mirrors, and we measured the wavefront error of that to be, for the front end, is about 3 nanometers RMS of defocus, 17 nanometers RMS of wavefront above that, and 24 nanometers RMS in the back end. However, there was the DMs deformed going from air to vacuum and at temperature. And so there was, after we had to do some optical adjustments and displacements of the optical elements on the front end in order to offset the that aberration, that deformation of the deformable mirrors, so that we don't have to use the actuator stroke of the deformable mirrors in order to fix self-flatten, and then on top of that have to flatten the rest of the the telescope, the CGI instrument, and then do EFC on top of all that. So after we did some corrections, we got down to 72 nanometers RMS above Z4. Z4 itself was 50 nanometers RMS. The Z4 could be corrected with the focus control mirror and still give us enough stroke to accommodate any other defocus from the telescope that we might expect. And then the rest would be corrected with the actuators on the DMs. Okay. So later on, we did in TVAC, we did post-flattening measurements using the prior to EFC, using the deformable mirrors, and the resultant wavefront, the flattened wavefront is 16.4 nanometers RMS, including defocus on the back end. Measured separately using a pinhole was 22.4 nanometers RMS, very close to the 24 that we had originally measured in air. Couldn't do the direct subtraction of that because of the pupil, the obscurations in the front end. But it's something that would be done on orbit. Okay, so for stray light control, we had a number of things to help control that. We use really high quality optical surfaces, the color filters to cut out out of band light, baffles, both standalone and integrated. We have a bladed stray light guard at the entrance with 3 blades there to help control any scattered light coming from outside the instrument. We have a light tight MLI enclosure, and we have continued contamination control monitoring throughout the INT process. The assessed stray light is in the dark hole is 2.73 photons per millimeter squared per second. That mostly includes a MUF of 3. In the case of radiation-induced luminescence, which is radiation causing the transmissive optics lenses at on the DPAM to fluoresce and produce stray light. We did not have the funds to do full testing of that, so we padded that with a MUF of 10 using the best analysis that we found on the variety of materials that are used for those optics. And we had one incident of stray light leakage during the testing. It was found that the diffracted out-of-band light after EFC would diffract into the field stop and would expand beyond the color filter, the size of each of the color filters. And it happened to be that we had gaps located around each of those filters, as you can see from this backlit photo. On top of that, we had removed the baffle sitting in front of the color filter alignment mechanism because we thought we needed the room for harnessing. So when we discovered this problem, and you can see here in this image where this crescent of light, that's from the outer band. This is a pupil image, but it's this crescent out here in the lower left that is the leakage. In order to fix that, we did analysis to determine if we put the baffle back in, if that would fix the problem, and also determine what size that baffle needed to be. So we went back and did additional stray light Fred analysis and found found that a baffle of this size, we found the right sized baffle. It's a racetrack, so any reflected light goes back through the baffle into a beam dump. And since we removed the original baffle after the optical bench had already been delivered, meant that the interface on the bench still existed. So all we had to do is fabricate a new insert for the baffle, and then mount the whole baffle assembly right up directly onto the bench at its original interface. We did not have a chance to test that, but all analysis shows that it won't be a problem. It completely blocks out the diffracted light from getting through those gaps around the filters. All right, I think I need to wrap it up. Optical throughput, here's a table here. The coatings of the optics alone for band 1, 60%. If we include the expected degradation loss due to contamination, brings us down to 51% by the end of our prime mission at 15 months after launch. And that's it for me.
Yeah, any time for just one question in the interest of time. Yes, Brian.
For the pans, do you know how stiff they are, and like structurally stiff they are, and what material are they fabricated out of?
I don't have that number in front of you.
It's the lightweight material with cities matching the beam mark, which is we have a library. The stiffness is we have like 100. The whole mechanism, including the moving part, is 100. Requirements 90 hertz,
Okay.
and we test about 120 hertz.
Okay, thank you.